Hi class. So we're going to start the next unit on color and shading. We've learned about color and shading before, but it was just the basics that we learned. And now we're going to revisit it and go a lot more into depth to give us more tools that we can use when we're choosing that pixel color for our fragments. Okay. Now where I'm going to start is learning more about color and intensity. Now, if you recall from an earlier lecture, RGB color, it's fake. Okay, it's faking real color. The way that it works is that you have these three emitters, red, green, and blue, that target your cones. But it's not natural. It's not how we think about color. It's not how actual color works. And this leads to problems. One of the problems is it doesn't actually match how we see. It's only an approximation. And a common example that comes up is green sensitivity. Okay, so in the real world, we're actually more sensitive to green than other colors, and that means we can differentiate shades a lot easier. We can see a lot more range in there than, for example, blue. That's not taken into account with the RGB model. Red, green, and blue are given equal value. Now, there are models where they give more bits to green to compensate for this, but it's definitely not standard. Another problem with the RGB color model is it doesn't match how we think about color. It's just not naturally how we understand color. So if you tell a friend, hey, what happens if you mix green and red light? Nobody knows, right? They don't understand what happens if you do that. You have to test it out. It's not how we think about color. So this leads to some problems. So for example, let's say you have a color in your game and you want to do something like, how do I change the shade? The color itself from more red into more green or more red to more purple without impacting, for example, the brightness. How do you change how vivid the color is? How about if I want to make it more vivid or less vivid, more washed out? How do you do that with the RGB model? Right? If I just reduce the colors, it goes to black. It doesn't become less vivid. So the RGB model doesn't really help us out. And the last thing I'll mention about using this RGB model in our display, this results in us having a limited gamut. Okay, so the gamut of the display is limited. That's a key word. Gamut just means the color range that it can reproduce. So I'm going to jump over to slides for a second. Give me a second here. I'm going to jump over to slides and we'll look at this a bit more. So here's an example here. There's nothing new here. Here's a picture. This is a common visualization. It can be hard to interpret, but that's okay. It's a color space, so it's a region of color. Now, you see green is big because humans can see a lot of variation in green. We're very well at discerning in green. Blue is really tiny. We're not good at blue. Now what this triangle represents here the typical monitor reproduction range. Monitors reproduce this range. There are a lot of colors that are outside the gamut of a typical monitor that's not being reproduced. Other models are listed here. CMYK is a printing model used with printers. Pantone's a different kind of model. It doesn't matter. The key point is realizing, oh, monitors aren't reproducing everything. I'll mention that there are wide gamut monitors, which helps to improve the situation, but it's beyond typically what people think about when they buy a monitor. Okay. So so RGB is great. It's what the world revolves around, but it has these caveats, okay? I should put that in my slide 2. It has these caveats. So it turns out there are many other color models out there. Many other color models that you're going to come across. And many of you have probably already come across them in your hobby or in other classes, okay? So we're going to learn a bit about them. Generally speaking, and you'll say that like 4 times now, it breaks color down into these dimensions, of course, but one of them is typically luminance. Now, luminance is just a fancy way to say how bright it is, basically. Okay, so how bright? Think about a light. How bright is the light? Well, the luminance of it, okay? And then we get two dimensions, two additional dimensions for color. So we pick our color in this two-dimensional space. You can imagine like a piece of paper and you can find your color. You pick your color in this two-dimensional space and then you add luminance to make it bright or less bright, okay? Now I'm going to explain how that works and you'll get some examples, but I'm going to highlight this. There's huge variation here. I'm going to highlight it in red. Okay, this is huge variation. There's so many standards, so many systems, so many non-standardized systems. Okay, there are many conflicting goals. Right? Are we trying to reproduce what humans can see? Are we trying to match the machine? Are we trying to make something that can compress well? Blah, 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 blah. There are system dependencies and so on and so forth, okay? One model I want to talk about that you probably haven't come across, but some of you might have heard of, and it's a nice model because it's actually really widespread, and it has a nice property that I like. It's called the YUV model, and it's not really used that much anymore, but for the longest time, this was the standard for color television. And there's a very historical reason for that. And it comes down to what the model does. So the Y, this is just my luminance channel again. And then, you guessed it, UV is a two-dimensional color space. Now, the reason why this became so popular is because when, eons ago, I actually used to have a black and white television, they came out with color TV and they wanted things to be backward compatible. So they used this model in color television, and this is how they did it. To be backward compatible. They had black and white televisions that would just broadcast intensity, luminance values, right? And it's black and white. It's just bright, and less bright, and black. Then they said, well, we'll keep that, but we'll add in these two color channels in addition. And if your TV doesn't read those channels, it won't even notice it. It's out of the spec, it's out of the space. But if you're a color television, you can add the color on top of that luminance. So it was backwards compatible. If you plugged YUV into a screen that was only expecting Y, it wouldn't even notice the UV. It would show you luminance. This is why you could put a color signal and show it on a black and white television in the old days. It was very nice. So this 2D space, you might be having difficulty visualizing what a 2D color space look like. There's a lot of different ones. This one, if I put U on this axis and V, Y, U, and V, then as you move away from the center, this is your saturation. So if Y and V are both in the middle, then it's going to be unsaturated or grayed out. No saturation, not vivid at all. All approaches gray. And then if I rotate my position using trigonometry, this is a UV color space, then this gives me the hue, which is the specific color. So if I want to go from red to green, I would have to rotate my color, which sounds weird, but this is just a two-dimensional number, right? U and V. I can use trigonometry, sine, and cosine to find a new spot in UV space. So this is all that YUV looks like. You have this two-dimensional space. Hue goes in a circle with saturation coming towards the middle. I will mention that there are several variants for various reasons in different systems, but we won't really get into them. Just be aware of that. So let's look at a slide. Okay. So here's slide 3. This is what UV looks like. As you can see, as you move towards the center, it grays out, right? It just grays out. You lose the color. It becomes desaturated. As you move to the edge, you get a color. If I want to move from red to green, I have to rotate in this space, YUV, okay? You should be familiar with spaces now. This shouldn't be too much of a stretch. All right, so that's YUV. That's all we're really going to cover on that. I'm also going to mention another color that you might actually come across. It's called LAB color. Sometimes it's written as CIE, big L, star, small a, star, B. I don't know why. But I don't know why those stars are there. There's probably a good reason for it. But L, maybe you guessed it, this is my luminance channel. I'm going to highlight this actually, LAB color. Is my luminance channel, but A and B are quite different than U and V. A actually goes from minus, which is green, to plus, which is red, and then the B goes from, I should probably make it all the same color. Then the B goes from, where am I? Minus blue to the positive, which is yellow. So it's just a different color space, okay? I won't really get into it, but the reason why we have LAB space is it's designed for artists and design. So it's designed for linear perception change. It's designed for how people work. Designed for linear perception change across the space. So if I think about my color space as 3D, LA and B, if I move a distance in any direction, I should get a relatively similar perceptual change to the person. Whereas in most models, like we saw green, you can see a lot. Blue, geez, I can move around a lot in the blue space and you won't see the difference because you're not that sensitive. LAB is designed to fix that. It takes the space, it transforms it and says, look, if I move a distance in the space in any direction, no matter what direction I go in, how I change the color, I should see the same amount of change, okay? So it's very popular in art and design. If you've used a lot of Adobe tools, you've probably seen this, okay? This is LAB color. And here's a visualization you'll often see. I find these visualizations kind of wonky. They're hard to get your head around. But what you want to gain in this is, again, we have on desaturated in the middle. So as you move away from that, you get saturation, but then you rotate. But you see here, it's not equal in every direction. And the reason for this is, like I said, we're really sensitive to green, right? So if I move a little bit in green, here, I won't really get to the next ball because I have such sensitivity here. Down in blue, a little bit, the same movement, I'll get to the next ball. So the clusters show you where you have less ability to differentiate, and the spread out shows you have more ability. So it's a nonlinear transformation of the color space. There's fancy math behind it. We don't want to worry about it. But it's focused on how you see, okay, and how keeping things linear. All right, let's go back to the iPad. So that's LAB color. Again, we're done. I'm not really going to go into that. Slide 4. Great. Now, I'm going to talk about another model, but this time I'm going to talk about a class of models, not just LAB, not just YUV. In general, we have these generic ones, and these are a lot less standardized. You'll see them called HSV, HSB, HSL, blah, right? Nobody can agree. Nobody can agree on how they exactly work. But let me talk about what they are. H is hue, which is our color, okay? H is hue, which is the color, red, green, blue, the shade, which is great. S is, so H for hue, S for saturation. How saturated the color is, whether it's washed out, gone to gray, or whether it's really vivid, okay? Maybe I'll put that in here, vivid. Or not, right? Whether the color is really full red or not red. And then this last one, well, this last one depends. It depends on which model you have, okay? If it's L, I should probably write this a little more neatly. Lightness often goes from black at no lightness to the full color when you're in the middle of the lightness. And if you keep increasing your lightness, it goes all the way to white. So you go black because it's really dark, you increase it and you blow it out. That's one way to do it. Okay, and then, actually I should write this here. Is a different in the other variant of the V variant, it's black at the bottom to full color. I'm going to show this visually. And B, I'm going to put a question mark because I've seen it go both ways, but typically, and we use it in processing, it's going to be this V model here. So again, this is highly unstandardized, unfortunately. And how to convert them specifically to red, green, and blue is also unstandardized. So you need to learn about the model that you're working in if you're going to be using this stuff. So here's an example. On the left here, we have hue. Again, you go in a circle, you can see hue, the color changes. Saturation goes from desaturated to gray to full color. And then the third dimension is lightness. So the L model goes from black when it darkens out to full color, and if it gets too bright, it blows out to white. Okay. This is perhaps how you might envision a camera might work. If it's too dark, it's black. If it's too bright, everything goes to white. Okay. HSV, on the other hand, it doesn't cap out at white, so it's almost like the first half of this one. Hue still goes in the circle, so if I go hue of 0, I forget where it is, but it's some color. As I increase it to my maximum, it's going to go around the circle. Saturation is desaturated to full saturation, and value goes all the way to black, all the way up. Now HSV, these models match a lot better the kinds of problems we were talking about earlier. If I want to change the hue in this model, I have H, S, and V. I want to change the shade of my color, but keep the same saturation and brightness. I can just rotate it. I just change the number of H, and everything else stays the same. If I want to change how saturated my color is without changing the brightness, I just change the saturation dimension. Okay. With RGB, you have to solve multiple ones in parallel. It's a little more weird to think about. So this is a very common model for like hobbyists, and processing can use it because it enables us to work with color a lot more closely to how we think about color. And here's the processing HSB model, where they give you this hue clearly goes from red all the way across here. Red 0 will be red, I guess. Roy G. Biv, right? And then you go around again. And saturation, you wash it out as you go this way, and then brightness goes to black or to this color. So if you imagine this going to black. I actually posted a demo you can play with this versus RGB. I won't be showing it because I'll be showing a different demo instead, but please do check it out. Okay, so that was my slides. Slides 5, 6. Okay. Now, like I said, HSV and HSB are really nice for how people think about color. Now, I'm going to show a demo. In the 90s, we had this problem where you had draw distance was difficult. If you increased your draw distance, the machine couldn't keep up, so you kept things drawn closely. One of the solutions they added to the games, so objects wouldn't just suddenly appear, right? When you got close enough to suddenly an object would appear in front of you, they added fog. Gamers hated it, but it was a way to let the machine have more complex scenes. You added fog. The way that we implemented fog was often just fading the object to the background color as it got near the edge of the back plane, so it didn't pop in. It would look like it would fade in. And we can actually do this quite easily using HSB, and this is what I wanted to show a demo of. So we can use HSB to easily implement fog. Okay, so I'm going to show my demo. All right, so I made this simple program. All that we do is we have a three-dimensional set of balls with random colors. So in my setup, I just generate some random colors. And then in my draw, what I do is I just draw these cubes of balls, you'll see. And what I want you to notice is that as we move away from the camera, we're going to introduce fog, okay? So if the fog is off, we just see balls going off into the distance. Excuse me. However, if we use in RGB mode, one way we can do this is we can slowly decrease the color until it matches our background color. In this case, we set our background to be 0.3, which is a gray. 0.3, 0.3, which is a gray. So what we do is, as the balls get further away from us, closer to that the far plane, we reduce the red, green, and blue by our scale value, which is calculated based on this Z value. We reduce them by scale so they get darker, and we cap them out so they don't get smaller than fog brightness. So they end up blending into the background. The problem with that is we're reducing red, green, and blue at the same time. The color slowly shifts a bit. It doesn't really gray out the way you'd expect it to with fog. Now we can do it. It works fine. but it's not the way we think about color. If I do it in HSV, I can keep the exact same hue, I can desaturate it, scale it down, and then also make it less bright, make it darker at the same time, but it shouldn't get darker than the fog, because then you'd see black spots in the fog. So we can think, let's keep the hue, let's desaturate, and move towards the fog brightness. So let's see what this looks like. Alright, so here's the balls going off into the distance. Here's RGB fog as we blend in, so it looks like it goes into the fog, which is kind of nice. But if I do it in HSV, you can see that you kind of keep the color more as you go into the fog, but it desaturates and goes. It just looks a little more less abrupt, and you get more of a depth effect to it. Now, what I've added in here is you can rotate the scene. Now, of course, the fog, we're rotating to look at the fog. So this is the RGB model, and here's the HSV model. So you can see you get that depth effect a lot nicer. Now, of course, you can do it with RGB too if you do the math right. It's not impossible. It's the same numbers, but in HSV, it's just simpler how to think about it. It's like, oh yeah, let's just desaturate and make it brighter, brightness go away, and so we can implement this fog. So download that demo and play with it. It's kind of fun. Okay, so that's all I'm really going to say about color. We'll come back and learn a bit more about intensity and brightness.